So today we launched the Carruthers Geocorona Observatory. It's NASA's first mission dedicated to studying the outermost atmospheric layer known as the exosphere. Now this region is truly vast. It originates near where most space stations fly and where most of Earth's satellites orbit the Earth, but then it extends almost halfway to the moon. Exosphere, because it's so vast and because it's so far away, we actually don't know how far it extends, to be honest. That's one of the things our mission will discover. Not just how big it is, but what shape it has, whether it's spherical or maybe it has a anti-sunward geotail formation. But most importantly, we want to know what is the density of the hydrogen atoms in this region, because interactions between those atoms and the rest of Earth's system play a critical role in Earth's recovery from space weather. Oh, so when a solar storm, it comes off the sun, and when they're aimed at Earth, it can engulf our planet and create extremely strong currents. And those currents can cause satellite charging, so they can damage satellite electronics. They regularly disrupt space-to-ground communication. This is our communication and navigation network, such as the GPS on your phone. And then also they can even disable power grids on the ground and have power outages. So they're very hazardous potentially, and being able to predict them in advance is what's going to help us protect both our assets on the ground and in space. Mars has an exosphere as well. It's much older than Earth's in the sense that exospheres are created ultimately through the evaporation of surface water. So liquid water evaporates, becomes water vapor. It gets broken down into its constituent hydrogen and oxygen atoms, and only hydrogen is light enough to reach the exosphere, where eventually it's lost to space. Now at Mars, this is how Mars lost its ancient oceans. Earth not only has much more water, but this process is much slower. But one of the things we don't know is how space weather, for example, affects the rate of this atmospheric escape. We also think that the fact that Earth has a geomagnetic field and Mars doesn't might play a role in helping Earth retain its own atmosphere. Well, the really exciting thing that we expect to get and see for the first time is a movie of Earth responding to a solar storm. So we're able to image the light that this upper atmospheric region gives off. And we need special cameras for that, ultraviolet cameras. And we need to be far enough away to be able to see the entire exosphere in one image frame. And so that's exactly what we're doing. That's why it's such a unique opportunity for us to be able to catch a ride share, essentially a hitchhike a ride, as a ride share mission of opportunity all the way out to this L1 Lagrange point 1,000,000 miles away, turn back and look at the Earth and take image after image that we then build into movies to watch how it evolves. It's so difficult and rare to get to this ideal vantage and to design a camera that can take ultraviolet pictures in such a wide field of view that only 4 pictures have ever been acquired before, and we'll be getting 4 pictures in our first 90 minutes on orbit.
And it's just a mere 1,000,000 miles away, just around the block, really?
It takes us close to 4 months just to even get there. Once we launch with our successful launch that we just had. But once there, we'll be on orbit for 2 years. But yes, it's 1,000,000 miles away, really special point in space where Earth's gravity exactly balances the sun's gravity. So it makes it really easy to maintain an orbit around this position. You don't need a lot of propulsion to get yourself back on track where you need to be in space. And so what that means is that we don't need a big propulsion tank in order to stay there for more than 10 years.